Welcome to Crash Course Astronomy. My name is Marco and I'll be your host for today's episode. We're going to be exploring one of the most spectacular processes in the universe, star formation. And I'll give you a spoiler. It's got nothing to do with interstellar birds and bees. You see, stars aren't eternal. They're born, live, and as all things, they eventually die. And right now, new stars are forming in our Milky Way and countless other galaxies surrounding. You can spot recent star formation by looking for young, massive O and B type stars. Now, I'm not talking about their blood types. These classifications of stars are short-lived, burning bright and fast, and are often found in glowing clouds called emission nebula. Their ultraviolet radiation excites the surrounding gas, making these nebula shine like a glove show. Stars form in cold interstellar clouds, primarily composed of molecular hydrogen. Star-forming regions, large ones such as the Tarantula Nebula, can host thousands of young stars in a single cluster. In fact, most stars don't form alone. They form in groups, which we call clusters. But how does a star actually form? Well, it all begins with gravity. A cloud of gas and dust collapses when gravity overcomes opposing forces, such as thermal pressure, magnetic field, and external forces. The thermal pressure small collections of atoms will disperse, roughly 10 to the 50th to start a collapse. Sometimes, an external trigger, like a supernova shock or radiation from a nearby massive star, nudges the cloud to collapse. As the cloud shrinks, it spins faster, thanks to the concentration of momentum, and suddenly, it'll flatten into a disk. Let's dive deep into how a star just like our own sun actually forms. We'll break this down into stages. Stage 1 is an interstellar cloud, a huge, cold cloud at about 10 Kelvin made of molecular hydrogen and dust. It's often triggered externally and fragmented into smaller clumps. These fragments will become their own star clusters. Stage 2 is a collapsing fragment. Each fragment, again made of hydrogen and dust, roughly 1 to 2 solar masses, shrinks under gravity while radiating energy efficiently, keeping those temperatures low. Fragmentation continues, producing more stars. Stage 3 is when fragmentation stops. As the density rises, radiation gets trapped, the core heats up, and a protostar begins forming with a defined photosphere. Stage 4 happens shortly after. The core reaches about 1 million Kelvin. There's no hydrogen fusion yet. The energy comes purely from gravitational contraction. The protostar is surrounded by a rotating disk of gas and dust collapsing upon itself. Stage 5 is the protostellar evolution. The protostar contracts, luminosity drops, core temperature rises to about 5 million Kelvin, and strong stellar winds emerge. At this point, it's classified as a T-Tauri star. In stage 6, we begin entering the newborn star era. Hydrogen fusion ignites at roughly 10 million Kelvin. The object officially becomes a star, with nuclear fusion now its main source of power. Stage 7 is when the star becomes a main sequence star. With core temperatures around 15 million Kelvin, outward pressure from fusion balances gravity. The star will stabilize and now spend billions of years on the main sequence. Basically, its adult life. Not all stars are created equal. High-mass stars form quickly, in about 1,000,000 years, while low-mass stars can take up to 1 billion years to reach the main sequence. A star's mass also determines where it lands on the zero-age main sequence, essentially the theoretical start of hydrogen fusion. Of course, we don't know this for sure. Observations closely match these predictions, and that reinforces our understanding of star formation. What about objects that don't quite make it as stars? Brown dwarfs are failed stars, with masses between 12 and 80 Jupiters. They're too small to sustain hydrogen fusion. They emit very little visible light, but may be as common as stars in the Milky Way. We can't tell, as we can't see them. Look at that little space intern. Shockwaves can play a big role in star formation. Explosions like supernova compress interstellar gas, triggering the birth of a new star. O and B-type stars, which form quickly, can create secondary shockwaves, producing second-generation stars. Observations confirm this. The youngest stars are near molecular clouds, while older stars are further away. Now that a star is born, its mass will dictate the rest of its life. A star's mass determines how hot it burns, how long it lives, and how it eventually dies. Most stars fall into a few major categories. The most common in the universe are red dwarfs. These stars have less than about half the mass of the Sun. They burn their fuel slowly and efficiently, making them dim yet cool compared to other stars. Because of this, red dwarfs can live for trillions of years, far longer than the current age of the universe. In fact, no red dwarf has ever reached the end of its life yet. Stars with masses similar to the Sun follow a different path. They spend billions of years on the main sequence, steadily fusing hydrogen into helium. When the hydrogen in their core runs out, they expand into red giants, shedding outer layers into space. What remains behind is a white dwarf, a dense, around Earth-sized object containing about half the original mass of the star. White dwarfs no longer fuse elements. They simply cool and fade over time. Heavyweights lead a different life. Stars with more than 8 times the Sun's mass live fast and die young. They burn through their fuel at an enormous rate, shining brightly, but only for a few million years. As they age, they fuse heavier and heavier elements in their cores, building up layers much similar to an onion. Once fusion can no longer produce energy, the core collapses, catastrophically, triggering a supernova explosion. What's left behind depends on how massive the core is. Some supernova leave behind a neutron star, objects that are so dense protons and electrons are crushed together, forming around a city-sized sphere with more mass than the Sun. Many neutron stars spin rapidly and emit focused beams of radiation, which we detect as pulsars. If the core is even more massive, the collapse continues, eventually forming a black hole. Gravity becomes so strong that light itself cannot escape. So what happens after stars have lived out their lives? They don't just vanish, they actually give back. As stars age and die, they return material to space through stellar winds, planetary nebulae, and supernova explosions. These events scatter elements like carbon, oxygen, nitrogen, iron, and silicon into the interstellar medium, the raw material for future generations of stars, and for us. You are not simply in the universe. You are made of it.